later today. You could work on it tomorrow. You could even work on it Wednesday, up until midnight, I guess, and then that's it.
Okay.
All of you guys somehow learned how to turn in your homework okay, because I got
Yeah.
it, and I put grades in the book. I still don't understand how you did it, but let me ask maybe Parker. Parker, how did you actually, which buttons did you push to turn in your homework? Did you have a scanner or a scan camera, or what did you do?
Well, first I took pictures of the assignment with the scanning app, and then I
The,
emailed
hang on, a scanning app. You had
email
a
on your phone.
you had a scanning app on your phone. I
Hmm.
bet everybody has that, don't you think?
Probably.
Okay, now keep going. I'm still listening.
And then I emailed the PDF to myself and downloaded it on my computer.
Oh, well, let me write some of this down. You had a scanning app and you took a picture of your homework,
Hmm.
and then you emailed that to yourself, right?
Yep. Yep.
Because other people will need to know how to do this. I guess they figured it out because I got all of them.
Yeah.
Okay, you emailed it to yourself. See, my daughter will understand all this. And then, then after you emailed it to yourself, then what?
And I just downloaded it onto my computer.
You downloaded it. You downloaded it to your computer,
Yep.
and then you went to Blackboard, right?
And then I went to Blackboard, and if you go to like before you click on a specific class, if you go to activity stream, you can see all the assignments that are due coming up. And if you click on one,
Yeah, you went to your assignment and you clicked on the assignment, didn't you?
yeah, it'll take you to the submission page.
Well, bless your heart. Okay, you guys are pretty good at this stuff. Hey, I've got some more customers here. I see Aubrey has joined us. Hello. I'll wave to you. We've got Stuart, Spencer, Roxana. Let me mark all these people here. Stuart, Spencer, Roxana, Megan. Uh, how about Bear, Aubrey, Cameron? Let me mark these down here. Let's see. We got Megan, Parker, Stuart, Bear, Aubrey, Roxana. How about Cameron? Is Cameron in the crowd here? Yes, Cameron, Spencer. What about Mohammed? Where's he at? I don't see Mohammed yet. He'll show up, I bet. Well, were there any? Let me tell you this. I put the answers to that homework that you sent me on content. Let me ask somebody there. Let's go to Aubrey. Aubrey, did you look at content and see the answers to that homework?
I haven't looked yet, but I did glance at it earlier and see that it was there.
But that's where it is. So if you want to see, if you got a 4, then you got it perfect. You don't need to look at the key there in content. But if I was mean to you and gave you a 2 or a 3, there was something I didn't like. So if you look on content, you'll see what I wanted.
Professor Griffin,
Yes.
for the scanning app, for homework, I
Yeah.
use Cam Scanner. You can find it in the App Store.
Oh, Cam Scanner. Cam Scanner. Yeah, keep going. I'm listening. Is this Aubrey talking
It,
to me?
and it's Megan.
Oh, I'm sorry. This is
It's okay.
Megan. I don't see a picture of you, Megan, but
No, I don't have one put up.
that's okay. That's okay, but I
Okay.
can hear you.
Yeah, so I use Cam Scanner and I really like it. You
Oh,
just go in, you can take pictures or you can take batches of pictures and it'll put
uh-huh.
it in a PDF form for you.
Yeah.
And you just email it to yourself, like Parker was saying.
Oh, okay. Good. Excellent. Cam scanner. All right. Any other comments before we jump into the exciting world of what are we studying today? Let me look and see here. It looks like we're studying PV diagrams for one thing. Any other questions or comments? Okay, well, let's talk about these PV diagrams because that's the big topic here. These PV diagrams kind of look like that. I think I already told you guys this, but this over here is called compressed liquid. I'm too lazy to write it. It's CL. Can you guys read my writing? Can you read that CL or is that too little? Probably too little. This is a saturated mixture here. See, that's liquid and vapor. Hey, there's Mohammed. He's with us now. Now over here, this is called superheated vapor. This little guy right here at the tippy top is called the critical point. If you're on this line right here, it's got a name. If you're on this line, they call that the saturated vapor. If you're on this line right here, that's got a name. It's called saturated liquid. You need to know all those names. There's a lovely picture of this in the book. Let's see if I can find the picture of it. Okay, yeah, here we go. I'm in yeah. There's a lovely picture of this on page 36 in your book. It's really a three-dimensional thermodynamic three-dimensional diagram. In my book, it's on page 36. The one on page 36 is for substances like water. There's another one on page 37. It's for substances like ammonia, but they're very similar. They are different. They even have another region down here where you have solids. In other words, if it's water, it would be ice. Now, what we're going to study today is how to do these PV diagrams for different processes. And we need to know what a process is. See, a process goes from one state to another. Like if you have state 1 and you have a process and you go to state 2. And we're going to put those processes on our PV diagram. There's also 2 other kinds of diagrams. There's a TV diagram. I'm not even going to do that. And then there's also a, let me think now, there's the PV, and there's a TV, and there's it's either a TP or a PT. Let me look and see if I can find that. But you don't need to do those. They have it's a PT diagram. They have a PT diagram on page 36 and 37, and they have a TV diagram, I think. Let's see. No, they don't have a TV diagram. I think they have some in the other parts of the book there. Yeah, there's one. They have a TV diagram on page 38. And they have some PT diagrams on page 37. All those are orthogonal views of a 3-dimensional structure. If you've ever taken drafting, there's a top view, there's a front view, there's a bottom view, and I guess theoretically 4 side views if you've ever had a course in drafting. And that's all we're talking about here, only we're just looking at the view of this 3-dimensional object where the pressure is up and down and the specific volume is going across. I don't know, read the book. It tells you about these thermodynamic diagrams. But that's what a process is. It's going from state 1 to state 2. Well, what do we mean by state? Well, in school, you probably learned there's 3 states. There's liquid, there's vapor, liquid, solid, and gas. I bet they taught you that in school. There's 3 states, liquid, solid, and gas. Well, in this class here, there's an infinite number of states, because if you change one property, you've got a different state. Now what a state is it's the sum of all of its properties. See, the properties are things like P, T, V, U, H, S, for example. Mass is a property. Those are all properties. And if you know all of these properties, you know the state. If you change 1 or 2 or all of them, you got a different state. See, if this is P1 and this is P2, and you can keep all the other properties the same. But if you change one property, you got a different state. If the pressure is different, well, you've changed it. That's what we mean by state in this class. It's not just liquid, solid, and gas, because you could have an infinite number of just liquids. All you got to do is change something about them, like the temperature. If you have two liquids and one of them has a different temperature, you got two different states. So now you know what state, the word state means in this class. And now we're going to talk about processes. Now, there's an infinite number of processes, but three of the big ones that we're going to study today are isothermal processes. We're talking about processes now. There's isothermal, there's isobaric, and there's isochoric. And we're going to do each one here in a few minutes. Now, the isothermal process is when you have a constant temperature. You have to follow a constant temperature. Isobaric process is when you have a constant pressure. Baric is, I don't know, Greek for pressure, okay? Iso means same. Thermal, these are Greek derivative words. Iso means the same temperature. Isochoric is that's when you have the same, you have a constant specific volume. So we're going to do all three of those. And here's something else you need to know. Not everything liquefies and turns to solid and it has mixtures. There's also ideal gases. Now the PV diagram for an ideal gas doesn't have this vapor dome, I call it. Doesn't. Can you guys hear me all right? Aubrey, can you hear me okay? Yeah? Parker, how about you? Can you hear me okay? Say yes. Yeah.
Yeah.
Great, great. Now I can tell you, for instance, what the isotherms look like on here. They go straight up and down, and then they come over here flat, and then they drop off like that. That's what the isotherms look like. Get yourself a red pencil, put your isotherms in red. But see, for an ideal gas, see, this is something here like water, for instance, or ammonia, or one of the refrigerants. But if you have an ideal gas, the isotherms go like this. These are the hot ones, and these are the cooler ones. Of course, these have hot ones and cooler ones too. See, there would be a hotter isotherm here. This would be the hot one, and this would be the cooler one. But there's these little sharp corners. There's these little kinks in the real substances, whereas ideal gases, they don't have that. They don't liquefy. They're just vapor all the time. And ideal gas isotherms look like that. Get your red pencil. Okay, do you have any questions so far? Okay, well, let's do a problem. We're going to do an isobaric. The first one we're going to do is an isobaric process. And I'm going to make some room here, and we're going to do an isobaric process. Here we go. But you guys are happy with all that?
Yeah.
Yeah, wonderful. Excellent. We're studying PV diagrams. The PV diagram is the secret to success in this class. If you don't get the hang of those, you're just going to have trouble. Okay, now this is problem 234. Let me find it in the book here, and we'll just have a good time working on it. And it's going to be an isotherm. No, isobar. Let me find it here. 234. Okay, I found it. Now they said it's saturated water vapor. They say it's saturated vapor. The secret symbol for that is FV, and I've shown you that. But whenever you see that, now they said it's 200 kilopascals. Whenever you see that, we're going to draw our PV diagram now. And we know where that is. It's on this line. Remember, this is the saturated vapor line. And if you have saturated vapor at 200 kilopascals, oh, you're in here someplace. 200 kilopascals. So you're right. You're right there. There's state one. We've just located it. And we're going to write down some properties for that. So go to the back, find water at 200 kilopascals. I found it. I'm going to write down some properties. At state one, the pressure is 200 kilopascal. They said so. The temperature is 120.23. Uh-oh, I'm running out of room here. It's degrees Celsius. Now I'm finding this in table B.1.2. I'm in table B.1.2. And I want to make sure that somebody out there is with me. So I want you to tell me what the specific volume is at state one. And go ahead. Anybody that wants to speak up, because I'm looking at it on my table. I know what the specific volume is. You tell me. I'll wait. I can outwait you guys. Can you get to the tables, you think? Somehow? You might want to make a copy of these water tables on paper. It's easier to get to paper. Now don't be shy. Parker, do you have the specific volume? of saturated vapor water at 200 kilopascals. Do you have that?
No.
That's okay. We'll pick on somebody else. How about my friend Stuart? Stuart, do you have it?
I'm trying to find it.
That's take your time. We can wait. It's table B.1.2, and you want 200 kilopascals. And we want the specific volume. It'll say VG is what it'll say. It'll say VG. We'll pick on Spencer. Spencer, can you find it yet?
I think I'm on the right table, but I'm still looking for the specific volume.
Okay. It says little V little g. See, in fact, it says saturated vapor above it. And you need 200 kilopascals over on the left.
Well, the furthest left column is the temperature.
Yeah. No. Flip a couple pages to where it has pressure as the furthest left column. Flip. Find the table that has pressure over on the left. It's easier. You could do it by interpolation, Spencer, on that table you're on, but it's easier if you'll find the table that's got pressure on the left. Can you find that?
Looking at it, it doesn't have, I'm not seeing 200 kilopascals. The lowest I'm seeing is 850.
Yeah, me too.
You can't find a table with 200 kilopascals?
Well, not on B.1.2.
Well, what table are you on?
B.1.2.
Okay. All right, if you're on table B.1.2, does it have pressure over on the left in kilopascals?
On the last section, but it starts at 850.
Starts at 850. Go back one page. There's 2 pages of that table. Spencer, you're on the second page of that table.
Well, that's still temperature on the furthest left.
Oh,
Yeah, for us, the last table is the pressure on the left, and the lowest is 850, and the highest is like 22,000.
yeah, I can see that one. The lowest is 850 and the highest is 22,000. But there's another table that the lowest pressure is 0 something and the highest is 800. And it's part of table B.1.2. It's a big old long table and it goes 2 pages long. And I know you've got it there someplace.
I see the one you're looking at. It's like 0.6113.
Yeah,
But-
that's the smallest. And the biggest is
that's-
8. Biggest
That's
is 8.
temperature.
No,
On the
that's
furthest left
pressure.
column is
The point
on
6.
my book, it shows temperature.
The pressure is 0.6113. The pressure is 0.6113, and at the bottom the pressure is 800. Does your table say that's the temperature?
Yeah, it might be an
Okay.
error in one of our books.
It's a screw up. The book has screwed up. The table, it should say pressure in kilopascals, and then it should say temperature in Celsius. And the temperature, it should be 0.01, and the highest temperature should be 170.43. I think the book has it labeled backwards.
Yeah, it
Yeah.
has it reversed on ours.
Take your virtual pen or pencil and cross that out. Yeah, this happened to my other classes. The book is screwed up. They don't want too many engineers out there. They're making it life hard for you guys. But they should have the pressure and the temperature. They've got them backwards. Now, Spencer, if you'll find 200 kilopascals, which they're lying to you, they're saying it's 200 Celsius, I guess. Now, can you find that little VG?
That would be 2706.63.
2706.63 at 200? It's not what I got. What'd you say it was?
This 2706.63.
2706. Man, I wonder what table you're on here. I have no idea where you are.
The reversing temperature and pressure, it's 200 kilopascals,
Yeah.
120.23 degrees
For the
Celsius.
temperature, right?
And then
Do they have
for
a little?
saturated vapor, it'd be the 3 columns over from that, right?
No, it's the first bunch of columns. They're just making life very difficult for us, aren't they?
Oh.
You were giving me
Well, I
the
went to the part
enthalpy.
that said saturated vapor. The
Yeah,
column that said saturated vapor, HG.
yeah. You don't want HG. You want VG, and that's the very first columns should be VG, and this should be 0.88573. Can you find it?
I don't see that anywhere.
It's not there.
Oh, I was on a different table. I found it.
All right. I want everybody to be able to find that, and I want you to label that. Those numbers there are little v's, and then the next numbers are little u's, and then the next numbers are little h's, and the last numbers are little s's. Now the book has screwed up, which makes me mad, and it ought to make you mad too. But that's life. But we finally found the little v, didn't we? Okay. Now let's go back to our problem. After you've all decided to switch your majors. All right. Now we're looking at those of you that are still with me. We're looking at problem 234. They don't make it easy, do they? And they said here, it has its pressure decreased to increase the volume by 10%. Well, we got our volume here, and we're going to increase it by 10%. Now, the way to increase that would be to multiply by 1.1 times your initial volume. People that have taken 5th grade mathematics, if you want to increase something by 10%, don't you multiply it by 1.1? Somebody say yes.
Yes.
Okay, well, we got V1. It wasn't easy, but we did get it. And so now I'm going to multiply that by 1.1. Here I go. I'm going to dog ear this page so I can get back to it. All right, 1.1 times 0.88573 is 0.9743. Those of you with calculators can double check me on that. Okay, now let's read on here and see what we're going to do. We're doing 234. 234, yeah. Am I doing the, no. I'm doing the wrong one here. What problem am I doing? Just a minute here. I'm trying to do 234. Yeah, right. Okay, I'm screwing up here, guys. I'm doing 236. Forget everything. Forget that. That's not right. But I think we're okay here. I think we've got our specific volume at 200 kilopascals for the water. I was reading the wrong problem. My apologies. And they said at this state, the piston is 1/10 of a meter from the cylinder bottom. And they want to know the temperature if the water is cooled to occupy half the original volume. Okay. Well, we can do that. Now, this is our PV diagram, and we're going to go to state 2. And at state 2, we're going to occupy half the original volume. So I was reading the wrong problem. My apologies. V2 is going to be half of V1. They said so. They said it's going to occupy half. So I can get that. Now help me do that and do that correctly. I could almost do that in my head, but I won't. Did you get 0.442? We'll just round it off. Well, here, 287. There we go. That's cubic meters per kilogram. So we've got V2. Now let's draw it on our graph. They said it's constant pressure, and it's going to have half the volume. So here's state 2. It'll be 1/2. See this distance from here to here? Isn't that about half? See, that's going to be state 2. And this is a constant pressure. We're going to just go like that, put an arrow tip on it, and that's our process. You're looking at the process. Here's state 1. There's state 2. And we've got the specific volume at state 2. And we know the pressure at state 2. It's the same. Well, it's supposed to be the same. It's supposed to be 200 kilopascals. Okay, now what do they want us to do? They want to know the temperature. Well, the temperature is the same. See, this is called condensing. And when you condense, it's like boiling. Condensing and boiling are also isothermal. The temperature stays the same. When you boil water on your stove, isn't it 212 degrees Fahrenheit the whole time it boils? Boil it for 10 minutes. The water level goes down and the kitchen fills up with steam, but the temperature of that water is still 212, right? So what is the temperature? Well, according to the table, it's 120.23. So there's your answer for the temperature. The temperature at state 2 is 120.23 degrees Celsius. We got the temperature. What else do they want to know? What is the temperature? How much is, well, to find this distance thing they're talking about, we're going to have to draw a device sketch. And I want you to start learning how to do device sketches. See, this is a PV diagram here, but we'll do the device sketch. Here we go. Okay, here's state 1. And here's your piston. And all you got at state one is vapor. See, there's no liquid. But at state two, here's the device sketch for state two. You got half the volume. Now notice we don't add any weight or take off any weight because it's a constant pressure. They said it was constant pressure. So you don't add any weight, that would increase the pressure. The atmospheric pressure stays the same, and the weight of the piston stays the same, so the pressure stays the same. But now you've got some water down here in the bottom. I got a blue pencil. Let's see if this comes out blue. Yeah, a little blue there. See, so you got a little water down here in the bottom. And then you have vapor, just like you have here. You have a saturated mixture. See, state two is a saturated mixture. Now, what are we supposed to do with it? What is the temperature? After volume. Well, I think we're done. I think we found the temperature. They wanted something about the distance. Well, guys, if this distance here is 0.1 meter, if the amount of the height of your piston is 0.1 meter, well, then this will be 0.5 meters. No, it'd be 0.05 meters, wouldn't it? Half of that. So there's your answers to problem 234. There's your PV diagram, and there's your device sketch at state one and state two. And didn't we have fun trying to find that in the tables? And we learned something, that the tables were mislabeled. We discovered that a couple of semesters ago. It's time you knew. Okay, we're gonna do a different one now, but before we go on, did you have any questions on that? While I've got that lovely diagram there, nobody has any questions. Well, I've got that there. Let me just tell you about something that you need to know. The reason why we do these PV diagrams is the area underneath the diagram means something. You see this area here underneath your PV diagram? Here, I'll kind of color it in. In this case here, it's a perfect rectangle. But it's not always a rectangle. It can be all kinds of weird shapes. But that area underneath that PV diagram represents, in this case, little w, the work per mass. And we'll show you that. And that would be easy to figure, because you know the height of the rectangle. It's 200 kilopascals. You even know the width of the rectangle, because see, this here is 0.8857, 88573. And this here is 0.44287, 0.44287. So you could get this distance here. If you know that and that, you just subtract them, and then you multiply by the height. I got enough room down in here. When you subtract these, I'm getting 0.44287 cubic meters per kilogram. If you subtract those, that's what you get. And then the height is the 200, I'll write it this way, kilonewtons per square meter. Now, when you multiply that, what you'll get is kilojoules per kilogram. And I'm going to do that. I got room over here. So little w, the amount of work per mass, turns out to be I'm getting an 88.57 kilojoules per kilogram, but now it's negative because you're not lifting something. See, if you lift something, that's positive work. But the environment is pushing down on you, on the piston or the system here. That's negative work. To help you remember, compression, this is compression. Can you see that? The piston's going down and you're compressing and you're condensing while you're doing it. That's negative work. If we were to expand, that's positive work. So try to remember, compression is negative work, or work per mass in this case, and expansion is positive work. Okay, great. That was fun. Now, were you able to get that 88.57? That negative? Yeah, I heard a yeah. That's the work done by the environment on your system. Okay, well, wasn't that fun? Do we have any other questions on problem 234? Well, I guess not. Okay. Well, let's do another one. Now that was a isobar. Let's do maybe an isotherm. That'd be fun. Here we go. We're going to do an isotherm. Let me make some room here. What we're studying today is PV diagrams and the tables. And we learned something about the tables. They're screwed up. Let me mention about the tables. When you go to those tables, they should have VF, VFG, and VG, and then the next bunch of things should be UF, UFG, and UG, and then the next should be HF, HFG, HG, and if I had room, I would write some others. Now, the book might have screwed up, and they might have this wrong. And over here, we were on the table that had pressure and temperature. I think the table in the book had temperature and pressure, if I remember you guys telling me that. But that's how they should go. This is how they should go. Okay, well, let's do another problem. Any question before I do a isotherm? Well, I didn't hear any questions, so we're going to do an isotherm. Here we go. But now we need to know what an isotherm is. Let me pick on my friend Megan. Megan, tell the crowd what an isotherm is.
Isotherm means constant temperature.
That's it. Good going. Good going. Now, the one I picked out to do with you guys is problem 2, 100E. And E stands for English. Okay, let me read it here and see what it says. 2100E. I found it. It says saturated water vapor. Now, I got a secret symbol for that. Instead of writing it out, I just go SV. Now they wrote it out and they said saturated water vapor is what they said. But I'm lazy and I just go S dot V dot. Now you must know where that is on a PV diagram. If we're dealing with water, it's going to have one of these things I call a vapor dome. It's going to look like that. And in this case here, we have 240 Fahrenheit. So we need the table that's got the temperatures on it. Shop with me in the English tables for 240 Fahrenheit. Okay, I found it. Now this is table F.7.1. See if you can find F.7.1. And what we need is 240 Fahrenheit. So it's kind of down in here someplace. Now, the temperature at state 1 is 240 degrees Fahrenheit. But the pressure is, and they said it's saturated vapor, so that puts it right there. Here's state 1. We need to read the pressure at 240 degrees Fahrenheit. Can you find that table, F.7.1, and tell me what the pressure is? Go ahead, I'll write it down when you tell me.
$24.968.
Yeah, that's what I got. 24.968 is the pressure, and that is in PSI. Now they said PSIA, but that A just stands for absolute, but all pressures in the tables are absolute. We don't need that little a there to remind us of that. Now we're going to get the specific volume. See, here's state 1 right here. It's right there. We're going to get the specific volume at state 1. Well, that's going to be equal to the little VG. I need somebody to, Cameron, are you with us, Cameron?
Yeah, I'm here.
Cameron, what is the little VG in that table?
16.3257.
That's what I got. Now these are cubic feet per pound mass. So we've got that. We know the temperature, the pressure, and the specific volume at state 1. Now let me go back and read the problem. We're trying to do problem 2-100E. It's in English. 2-100E. I got lost. There it is. Oh, this says they're going to have the pressure decreased, but they're going to increase the volume by 10%. Okay, I think that was what I was starting to do last time and got mixed up. We're going to increase the volume by 10%. So, a little room over here. Here we go. V2 should equal 1.1 times V1. That's how you increase something 10%. You multiply by 1.1. Okay, well, I'm going to do that. Here goes. Now, let me dog ear this page so I can find it again. Okay, here's V1. We got that. That's 16.3257. We're going to multiply by 1.1. Did you get 17.9583 cubic feet per pound mass? Well, we think we know V2 now. And did they say it's a constant temperature? Yes, it's an isotherm. Now, do you remember how isotherms go? They go like this. Now they're just flat in here. Because see, that's evaporating or boiling. When you boil water, the temperature stays the same. Now here, all the water, there's no more liquid now. Now it does that. Okay, now this volume right here is 16 something. 16.3257. But see, we're going to increase it, and here's our volume now, out here someplace. It's state 2, and at state 2, it's 17.9583. Here's state 2, and here's your process. This is our process. Put an arrow tip on it. There's state 1. There's state 2. We're going to go from 1 to 2. There's our process. That's the process. Now going from 1 to 2, this process has got a fancy name. It's a special kind of process. Let me pick on my friend Aubrey again. I'm always picking on you, Aubrey. What's the name of this process going from 1 to 2? It's got a fancy name. It's called...
I'm not sure.
That's okay. We'll pick on somebody else. There's thousands of different kinds of processes, but the ones we're studying today are the ISO something and the ISO something and the ISO something processes. Aubrey? Yeah, you can do it. I'm going to help you. There's 3 kinds of processes that we're studying today, and they all start with ISO.
Is this the isothermal one?
That's it. Good going. See, you can do it. This is an isothermal process because it follows the isotherm. See, this is an isotherm. I put my isotherms in red. You know what? This is the same isotherm. It's the same isotherm. And it happens to be 240 Fahrenheit. You know what the temperature is right here? It's 240 Fahrenheit. You know what the temperature is here? It's 240 Fahrenheit. You know what the temperature is here? It's 240 Fahrenheit. What's the temperature any place in here? Well, it's 240 Fahrenheit. What's the temperature there? 240 Fahrenheit. What's the temperature here? 240. You know what? It's 240 Fahrenheit everywhere on that red line, because that's the 240 Fahrenheit isotherm. It almost makes sense. But now what do they want us to do? Let me read this again here. We're doing problem 2-100E. They want to know the pressure. We know the temperature. We know the specific volume. It's 10% bigger. We understood all that. But see, the pressure is going to be different. Now, what's the pressure here? Let's get this pressure. Go back to your tables. I've lost my page here, but I dog-eared it. And at 240 Fahrenheit, whoops, I'm in the wrong table, just a minute. 240 Fahrenheit, I know what that pressure is. I'm going to pick on somebody. How about my friend Bear? Bear, are you with us? Unmute, Bear.
Yep, I'm here.
Tell me what this pressure is, Bear. You need to be on table F.7.1, and you need to look up 240 Fahrenheit and tell me what the pressure is.
F.7.1.
Yeah, F.7.1.
And what'd you say on the temperature?
240 Fahrenheit.
All right. The pressure for it is 24.968.
Good going. Excellent. 24.968. Now that's PSI.
Yes, sir.
Pound, yeah, good going. Pounds per square inch. Now, can you guys see that state 2 is going to be smaller than 24.968? See here, this is the way the pressure goes. It gets bigger going up here. Higher pressure up here, lower pressure down here. Well, can you guys see that state 2 is lower than state 1? See, here's state 1. Here's state 2. Pressure got lower. They want to know what the pressure is. Well, how are we going to do that? Well, you can't use the ideal gas law. You know, PV equals RT. How come we can't use the ideal gas law? Because it's not an ideal gas? That's a pretty good reason. It's not an ideal gas, so we're not going to use the ideal gas law. So what do you use to find the pressure? Well, you use the tables. So we're going to try to find the pressure. Now, this is going to be hard and ugly, but we can do it. But you know, this region out in here, this is called saturated mixture. This is called compressed liquid. What do they call this region out in here? It's got a fancy name. Pick on somebody here. How about my friend Roxana? Roxana, unmute. Tell me the name of this region out in here. See, this is saturated mixture in here. Compressed liquid over in here. What do they call this, Roxana?
Superheated
That's
vapor.
it. That's it. It's superheated vapor. So which table should we use? Now let me think. Should we use the saturated mixture table? No. Should we use the compressed liquid table? No. Hey, I got it. Since it's out here in the superheated vapor region, why don't we use the superheated vapor table? Does that seem reasonable? Okay, let's find it. Superheated. Hey, here's one. And I'm going to try 20 psi, and maybe we'll get lucky. Here we go. Now here's what we know. We have the specific volume. It's right here. Let me do it up here. We know V2 is 17 something. And we know we want to find P2. But we do know T2. T2 is 240 Fahrenheit. We've got to find P2. It's going to be ugly, but I need some room. And you guys are taking excellent notes, so I can erase this. That's just the saturated vapor specific volume that we looked up in the table. Okay, we got to find P2. Well, I'm going to try a 20 psi, and maybe I'll get lucky here. At 20 psi and 240 degrees Fahrenheit, the specific volume is 20.475. Cubic feet per pound mass. I'm getting this out of the superheated vapor table, table F.7.2. See if you can find it. Anybody found it? Now at P1, see P1 is 24,968. At 240 Fahrenheit and 24,968 psi, the specific volume is 16.3257. We want 17.9583. Well, you know, that's in between these two numbers. Looky here. We want 17.9583. We want this missing P2 here. I'll put it in kind of a mystery cloud. You see, we're going to have to interpolate the tables to get it. Everything here is at 240 Fahrenheit. We know that the temperature here is 240 Fahrenheit. Temperature here is 240 Fahrenheit. But this is what we had at state 1. State 1 was 16.3257. State 2 is, I got lost here. Where did I get my state 2? I was doing, oh. No, that's the pressure. That's the specific volume at state one, isn't it? No, guys, I just had a senior moment. Let me have a sip of water here and we'll figure this out. I think I did everything right so far. But this is kind of tricky. Oh yeah, yeah, I got this from the tables at 20 psi, and this we got was at state one. Okay, I'm still confused. At 20 psi. We had 20.475 and 24.96. That's state one, isn't it? No, that's state two. Okay, guys, I'm totally confused. Is anybody else out there totally confused? No. Okay, I just need to write this in a way that'll make sense. Okay, let me try writing it in a way that'll make sense. Okay, we're going to write this in a way that'll make sense. Okay. We know the temperature at state one and at state two is 240 degrees Fahrenheit. We know that. What we don't know is the pressure. Now, we're going to put the pressure, we're going to have 20 psi and the pressure at state two, which we don't know. And then we're going to have the 24.968 psi. But no, wait a minute, that's at state one, isn't it? State one, we have 24.968 psi. State two, we don't know. This is state one. We don't know the pressure at state two. That's what we're trying to find out. But now let's write down the specific volumes. Maybe I should write those down. The specific volume at state one is 16.3257. And the specific volume at state two is 17.9583. Okay. Okay, we know that. Now the pressure at state one is 24.968. We know that. And the pressure at state two, we don't know. We don't know what this pressure is at state two. Let me put this in the middle. Yeah. I'm getting the hang of it here, I think. See, we don't know the pressure at state two. We'll put a question mark on that. But in the tables, when the pressure is 20, see, that's down here someplace. I'll put it here. When the pressure is 20, psi. The specific volume is when the pressure is 20 psi. This at 240 Celsius, the specific volume is 20.475. Can you guys see that 17.9 is in between 16.3 and 20.475? So our pressure that we want at state 2 will be in between 24 and 20. See, we got these from the tables. Maybe that makes sense to somebody out there. We're trying to find this pressure at state 2. We know it's in between 20 and 24 because the 17, which hopefully you all understood, is in between the 16 and the 20. Before I interpolate this, does anyone have any question about where I got each one of these numbers? Ask, and I'll tell you where I got the numbers. Nobody's going to ask me. So I assume that you know where I got all these numbers. Let me ask. Go ahead.
Looks all right.
Okay, good. Excellent. Here, let me ask you to make sure that we're connecting here. You see that 16.3 blah blah blah? I got that from someplace. I'll pick on somebody. Mohammed, where did I get that 16.3257? Where did I get it?
Yeah, I'm looking to with the
See-
table, but I didn't find it.
See if you can find where I got that. We're asking,
Yeah, I'm with it.
where did Mr. Griffin get 16.3257? Where did he get it? And we're picking on Mohammed.
Yeah,
right
it's
now.
yeah, it's in the volume.
Yeah. And what
Specific
table is it?
volume. 7.2 F.72.
Well, I'm on table F.7.1. I don't think you want F7.2. Wait, I guess, wait a minute. I think you could get it F7.2. Just a
Yeah,
minute.
right.
Let me see. No, I think, Mohammed, I think you need to be
Yeah.
on F.
I went back to the F.7.1.
Dot one, yeah, F.7.1, right? Is that what you
Yeah.
said? Yeah, that's where it is. If you look at that table and look up 240,
Yeah, that's
there it is. There, that's where I got that. Now, as long as I'm picking on Mohammed, how did we get to 17.9583? Do you remember how we did that?
second.
How did we get
No.
that?
I don't know.
That's okay. That's an honest answer. I like it. We multiplied by 1.1. Now, why did we multiply by 1.1? Anybody? Let's pick on somebody else. Cameron, why did we multiply by 1.1?
You're adding 10% to it.
That's right. We took the 16.3, multiplied by 1.1, and we got the 17 point blah, blah. As long as I got Cameron on there, I'll pick on Cameron. Cameron, where did we get this 20.475?
That's from table F.7.2.
Yeah, that's right. It's from
And
the
it's the,
superheated vapor table.
yeah.
Okay, now what we're going to do is we're going to get the answer, and we'll be through with this problem, and we'll do another one. But to get that answer right there, you have to interpolate, because see, this number is in between those two numbers. So this number will be in between those two numbers. Now I'm going to shut up for 2 minutes. And I want every one of you guys, this is a participation class here. By the way, I think your test becomes available. I think it is available. And it's not due until midnight Wednesday night. That's your first exam. So don't turn off your, don't turn me off. Now let me finish my wonderful lecture here. But you guys can get started on that. All right, now, here goes. I'm going to do this. I want you to do it. I'll shut up. Find P to interpolate. Go for it. Can you read my writing? That's supposed to be an 8, I think. All right, go for it. Well, I might be rushing you guys, but I gave you maybe a minute and a half. I think I know what this P2 is. Anybody want to tell me what they got for P2? What did you get? Spencer, did you get anything yet? You're still working.
I just wrapped up. I got 21.955.
That's wrong, Spencer. We'll write it out here in a minute. Spencer, I think what you did was, did you notice that these numbers are getting smaller? They're getting
Yeah,
smaller.
I did. I should have subtracted instead of adding it to the 20.
Yeah, I think that's what happened. If it's not too late, maybe you can go back. I bet you did part of it right. What about my friend Stuart? Stuart, do you have that yet?
I got a 23.9612.
Now that's closer to the right answer, but that's still not what I got. Now, you might be right, Stuart, and I might be wrong, but that's not what I got. Somebody else. How about Roxana?
I got 23.013.
That's what I got. And Roxana, I got your email, and I think I fixed the situation.
Okay, thank you.
Thank you. And if ever I cheat anybody, you let me know, and we'll make it right. I'm getting 230133 maybe. Anybody else getting that?
I got that.
Yay! Well, there's three of us. I think that's the right answer. Okay. Now, you know what we did not do on this problem? We did not make a device sketch. I need to make a device sketch. Wonder if I got enough room to make a device sketch. I just don't have enough room here. We'll make room though. We're gonna make some room. We all know it's June 8th, right? We don't need that. And we know what we're studying. We're studying PV diagrams, learning how to use the tables, learning that they've screwed up the tables to make life difficult. And we all know what SV stands for now, I hope. So look at all the room we have. And we're doing problem 2, 100E. E stands for English. All right, now we're going to do our device sketch. Here we go. Here's state 1. And here's state 2. And here's state 1. And in state 1, it's saturated vapor. That's what that is right there, saturated vapor. So there's no liquid. It's just all water molecules, right? But what will state 2 look like? That's a good question. Well, I want to move on, so I'll just go ahead and tell you. See, we're going to take some of the pressure off. The pressure is going to drop. The final pressure is going to be 2301. So we're going to drop down to 230133. We're never going to get to the 20. We just use that. See, it's down here someplace. We just use that from the table so we could interpolate. We interpolated between these two, and we found the pressure went down. So we took a little weight off. So here, put a little weight on here. We're going to take it off. Now, when you take that weight off, you know what happens? The pressure is smaller. There we go. But it expands. Does that make sense if you take that weight off, that it expands? Now, what about the temperature? Well, the temperature stays the same. Now, how are we going to keep that temperature the same? I got an idea. 240 Fahrenheit. Man, that's pretty hot, isn't it? Isn't 212 boiling at standard pressure? 240 is even hotter than boiling. Okay. I'll tell you what we could do. We could put this in a bucket of hot oil. Put it in a bucket of hot oil at 240 degrees Fahrenheit. And then later, this is at state 2, it's in that same bucket of hot oil at 240 degrees Fahrenheit. I don't know, get some vegetable oil or Crisco, heat it up on the stove till it's 240 with your thermometer. Take some of the weight off and it'll expand, but do you understand it'll stay at the same temperature, won't it? It'll stay at the same temperature. Interesting. It'll stay at the same temperature. Now, we talked about work. This is expanding, going from here to here. They call that expansion. See, going the other way, that problem we did earlier was compression. The volume got smaller. Well, this volume's getting bigger. And do you remember, if you expand the work or the work per mass is what? Is it positive or negative? What do you think? The work, when you expand, is
Positive.
It's positive. Now, you can talk about big W if you want. Big W is just the mass times little w. Little w is the mass per, the work per mass. When you compress, the work is negative. Now, we'll show you how to calculate that work later. I'm not going to show you right now because right now we're studying processes on a PV diagram and how to read the tables. We're reviewing how to interpolate in the tables. That was kind of tricky. I don't know if I kind of got lost there for a minute. What else are we studying? Device sketches. They call these device sketches. The key to this course is the PV diagram, putting the process on there. Hey, look, there's the process. See that 1, that 2? And there's the process. And it's going from 1 to 2, and there's an arrowhead telling the direction. That's the key. But it's also very helpful to draw the device sketch. And we did that. Okay, now let's see. We've done an iso bar and an isotherm. We're going to do an isocore next. The next little project is an isocore. Okay. I'm going to erase all this and we're going to do an isocore. Oh yeah, one last thing. I didn't draw this, but if you took the area under this graph, now the trouble is this is not a straight line. It's a curve, right? It doesn't look like a curve, but it is, okay? The area underneath this kind of looks like a trapezoid, but it's not, because trapezoids all got straight lines. They don't have curves. But the area underneath that, here, if you colored it in, there you go, color it in, it represents something. What does it represent, Parker? What does this area underneath this process represent, Parker? Earth calling Parker. That area represents.
Per mass.
So say that again, Parker.
The work per mass.
You're right. It's a little w. It's the work per mass. Exactly. We're going to show you how to do that coming up, but not right at the moment. Now, if you had a P big V graph, we don't. We have a P little v graph. But if you had a P big V graph and you had an area under here like that from 1 to 2, that area is big W. Do you understand? But if you have a little p little v, that area is little w. It's the work per mass. But if you have a P big V graph, it's big W. Any last comments before we do an isochore? Well, nobody said anything, so I'm going to erase all this and we're going to do an isochore now. Now you also have some homework. You have an exam and homework. I forget what the homework is, but it's due Wednesday night at midnight too, I think. You can look it up. I could tell you what it is. But what we're going to do right now is an isochore. Now, I told you what isochores were. Megan, I'll pick on Megan. Megan, what's an isochore?
An isochore is when the specific volume is constant.
Yay, good going. Good going. Now, this particular isochoric process is 241. We're going to do problem 241. Now let me find it here. Let me shop around. Find 241 here. I found it. Now this says R134A. R134A. That's what you guys have in your car air conditioner. I bet every one of you guys has a air conditioner in your car. Well, it's got refrigerant 134A in it. I want to look that up here. Let me see if I can find it. R134A. Yeah, here it is. This is in Appendix F, as in Foxtrot, and it's CF3, CH2, F. That's the molecular formula. It's got a fancy name. It's called tetrafluoroethane. And this, I found this on table F.1. What this is, it's got a fancy name. It's called I forgot. Something like halogenated ethane. I think that's the fancy name for it. See, you start off with ethane. A little bit rusty on my organic chemistry here. And what you do is you replace 4 of those hydrogens with fluorine atoms. So we're going to take 1, 2, 3, 4, and replace them. Now there's your structural formula for refrigerant 134A that you have in your car. Now, wasn't that interesting? I'll never ask you that again. You don't need to know it. Forget it. But that's what it is. And let's go back and read our problem now. It's 241. It's in a sealed rigid vessel of 2 cubic meters as saturated vapor. Let me write that down. It's R134A, and it's saturated vapor. Do you notice I put a PV diagram right off the bat? So go to the back and find, now this is at 50 degrees Celsius. Go to the back and find R134A. Start shopping around. Well, I guess on your phones or however you do it. Okay, I found it. R134A, and it's saturated. Now, do you know where saturated vapor is? Let me pick on my friend. Cameron, where is saturated vapor, Cameron?
It is saturated vapor.
Yes, where is it on this graph? On this PV graph, saturated vapor is at a very definite spot. Where is it?
I guess I'm not too for sure. I guess I didn't write good enough notes.
Well, that's okay. You're here to learn. And I think this is important that you know where saturated vapor is. Let me tell you where it is. It's anywhere on this line. You see this line right here?
Yeah.
They have a name for this line. It's called the saturated vapor line. We're on that line someplace. Now to find where, we'll just go to the back and find R134A. And they've got pressures down here at the bottom of 8.3 or something like that, and 4,000 something up here at the top. The tippy top is 4,064 kilopascals at the very tippy top. But and that would have a temperature, by the way, of 101.2. Here, I'll go ahead and draw that. They call this the critical isotherm. It's 101.2 degrees Celsius. But see, what we are at is 50. Well, 50 is around in here someplace. There's your 50 degree Celsius isotherm. I'm on table B.5.1. I'm on table B.5.1. And now I know exactly where I'm at. I'm right here. There's state one. That's state one right there. It's on the saturated vapor line, and it's at 50 degrees Celsius. There's state one. Now let's keep reading. And it says, guys, if you just woke up from a daydream, we're doing problem 241. And it says, saturated vapor at 50 degrees. It's got 2 cubic meters. Let me write that down someplace. 2 cubic meters, rigid vessel. In other words, it's not a piston cylinder thing. It's a rigid vessel. Okay? There's state one. Here's state two. There's no piston. The volume's not going to change any. So let me read this. It says, now we're going to cool it to 20 degrees Celsius. Well, let me draw 20 degrees Celsius on here. That's colder, isn't it? I might have to fudge a little bit to get this in here. I just needed some room to fit this in here. So 20 it would be colder than 50, so it's kind of in here someplace. And so there's a 20 degrees Celsius. 20 degrees Celsius isotherm there. But we have to follow an isochord. We have to have a constant specific volume. Well, the way we're going to do that is we're going to go straight down. Here's state two. Here's state one. Notice we didn't change our specific volume any. We went straight down. Well, there's our process, guys. You're looking at it. The process goes from 1 to 2. Straight down. Because it's an isochord. Notice, I didn't draw this very good, but the idea is that the volume doesn't change any. And you got, it's all vapor, saturated vapor. Wait a minute, auga. Something happens going to state two. Can you see that you're picking up some liquid here? I'll make it blue to kind of give you an idea of some liquid there. But at state two, you have part liquid and part vapor. Now they have a special name for that when you have part liquid and part vapor. We'll go to my friend Aubrey again. Aubrey, what do they call it when you have part liquid and part vapor? What do they call state two, Aubrey?
A saturated mixture.
Yay, good going. It's called a saturated mixture. Now, I call this thing here the vapor dome. That's what I call it. But your book calls it the saturated mixture area of your PV diagram. It's part liquid and part vapor, and you're at state two. And what do we know about the specific volume at state two? Well, we said specific volume is constant. Wouldn't it be the same as what you have at state one? Yeah. Well, what is the specific volume at state one? I'll shut up and I'll let you look it up. Look up the specific volume at state one for R134A at 50 degrees. and tell me what you get. Anybody? It's on table B.5.1. You got to go to table B.5.1 to find the specific volume of saturated vapor at 50 degrees Celsius. What is it? I know you guys can do this. Bear, pick on Bear. Bear, what's the specific volume at state 1?
The specific volume?
Yes. It's state 1. I'll give you a hint. It's saturated vapor. So it's right there. It's the little V sub G in the table. What's it say?
0.01512.
That's what I got. That's exactly what I got. I got 0.01512. There it is. Well, you know what? That's at state 1. And that's what is that? What is that? Cubic meters per kilogram. But see, that's got to be the same at state 2 because it's an isochore. Now, here's what I want you to do. I want you to find the quality at state 2. Let me make a little room here. Yeah, there's some room down in here. There's some room. I'll shut up for 2 minutes, and I want you to find the quality. They call that quality. It's state 2. Now here's how you do it. The specific volume at state 2 is equal to VF plus the quality at state 2 times VFG. But see, you're going to have to look up at 20 degrees Celsius in order to find this. You'll find, we already know what this is. It's 0.01512. These you can look up in the tables. And I want you to find the quality at state 2. And I will shut up for 1.5 minutes. In fact, I haven't given you guys any break at all, have I? I'll shut up for 10 minutes. Go ahead and solve that and take a 10-minute break. Go get yourself whatever you do, a glass of water, something, stretch. We're having a 10-minute break. And when we come back, we're going to get the quality and then we'll answer whatever they wanted. I don't know what it was, but we'll figure it out. Okay. 10-minute break, guys. No, they got another hour. Another hour. They have a 10-minute break. Yes, bud.
Can you fix my tiny breakfast?
I would love to, but I can't. I've got to start this class back in about 5 minutes.
Could you pour me a glass of orange juice?
I would love to, but I bet. See if Nana can do it. See if you can get Nana to do it. Well, your 10-minute break is just about over here. We are doing problem 241. What do they want us to do? They want the mass and the quality. Okay, well, let's do that. Let's get the mass and the quality for them. I just need a little room to do that. Now, if you want the mass, you could get the mass by taking the volume and dividing by the specific volume. They said in this problem that we're doing problem 241 and our 10-minute break is over. Welcome back, y'all. Wait a minute, where is everybody? I think I'm missing somebody. I'm missing some of my friends. Hey, they're coming back. They're coming back. Let me check the roll here and see if I got everybody on here. I just like to know who's there and who isn't. I think we got everybody. I think everybody is here. Yeah. Okay. All right. Well, we're doing this problem 241. And the thing is, they told us what the volume was. They said it was 2 cubic meters. Here, I'll put those units in brackets. See, what's confusing is that M there doesn't stand for meters. That stands for mass. But that M there stands for meters. But see, when I put my units in brackets, that's my secret signal that we're dealing with units, not algebraic variables. Hey, there's another customer. Okay, now the specific volume at state 1, and the volume at state 1 and the mass at state 1. Of course, the mass doesn't change. In fact, nothing changes. The volume doesn't change. It's 2 cubic meters. It doesn't change. It's fixed. The specific volume going from 1 to state 2, it doesn't change because it's an isochore. And so the mass doesn't change. Whatever mass of refrigerant you have in here is the same before and after. And our specific volume at state 1, I think I erased it. But I can find it again, I think. I just go to my table. And we'll look up 50 degrees. And it says here, I don't remember. Yeah, there it is. Oh, there it is. It's right under my nose. I didn't need to look that up. It's 0.01512 cubic meters per kilogram. You see the cubic meters cancel, and you're left with kilograms. Okay, here goes. We're going to get our kilograms now. Hey, there's Bear. You're actually, I got the picture. Hey, I got a picture of him on here. Okay, well, here goes 2 divided by 0.01512. Well, I'm getting the mass at state 1 is the same as the mass at state 2, which is 132 point, rounded off to 3 kilograms. So we got the mass. Now we're going to find the quality. They wanted the quality on this problem. So we know V2, it's the same as V1. It's 0.01512. But VF, I'm going to have to look that up. Okay, let me shop around. But see, now what I want is at state 2. That's at 20 degrees Celsius at state 2. Well, at 20 degrees Celsius, okay, now just a minute. Yeah, here it is. 20 degrees Celsius. We're going to have to look up this VF thing, and it's 0.00817 plus x2 times VFG, which is at 20 degrees Celsius, 0.03524. Can you find those numbers in table B.5.1. That's where I got them from. All right, now I'm going to get the quality at state 2. Here goes. Well, I got a quality at state 2 of 0.1972. That's it. We found the quality at state 2. Well, let me show you some other little things here. Namely, I just don't have enough room to work here is my problem. But we're doing problem 241. We did problem 241. What about
Professor Griffin?
Yeah, go ahead.
For VF, isn't
Uh-huh.
it 0.000817?
Oh, we thank you so kindly. I think you're absolutely right. Let me dig here. R134A at 20, it's 0.00. You're absolutely right. Now, was that my friend Megan? Is that who that was?
Yeah.
Megan, you were absolutely right, and I was absolutely wrong. I don't think it's going to make a heck of a lot of difference, but it'll make a little, so let me do it right this time. But I appreciate you, and I'm going to put a nice happy thank you point up there for you. 0.01512 minus 0.000817 divided by 0.0. I got the other numbers right though, right, Megan? Where's my answer now? I got lost. Well, that's wrong. Something bad happened. Let me do that again. I must have done something wrong. Gee, I didn't get this answer at all. I don't know what happened, but something very bad happened. Did you guys get 0.4059?
Yeah.
Yeah.
I don't know what I did. Who knows? I pushed the wrong button someplace. I'm so glad that Megan spoke up. I don't think that made the big difference. I think I pushed the wrong button someplace. Hey guys, if you got any question and it's not working out for you, you speak up. Because I pushed the wrong button. But I think we're okay now. Anything else, anybody? Well, okay. Now let's do the little W again. That'll be fun. The little W. What is the work done? You know, I told you about expansion work and compression work. Well, guess what? Nothing's expanding and nothing's compressing, right? So what's the work? It's not expanding. This is a rigid, fixed volume vessel. It's not getting bigger. It's not getting smaller. The volume stays the same. So what's the work? Or the work per mass? Go ahead, be brave. Tell me what you think. Bear, what do you think? What's the work?
Would it be the evaporation?
Well, now, work is when you move something with a force. Evaporation is a little different concept. But Bear, in this case here, nothing is moving. There's no force moving anything. So what's the work? That's okay, Bear. You're going to get this stuff. But see, the work is zero. There's no work. Do you remember before we had a piston? And I think on one example, the piston got bigger. The piston got bigger. Well, that's work. You're doing work when you lift stuff up. And I think in one of our examples, the piston got smaller and we got negative work because the environment was pushing on our system and compressing it, and we had negative work. But here, we're not expanding and we're not compressing. It's just a fixed volume. There's no work done. Bear, you were supposed to say, Mr. Griffin, the work is zero. That's what I wanted to hear. Do you understand?
Yes, sir.
Good deal. Excellent. Good deal. Well, let's talk about work, if that's okay. If you guys are happy with all that, and you have your homework, I think your homework is 236 and 238, plus your test. But none of that's due till midnight on Wednesday, so you could put it off. There's no use in getting started yet, is there? Well, let's talk about work a little bit. I've got a little of your time. I've got 35 minutes of precious time with you. And we're going to talk about work for a little bit. But there was no work at all on that isochore. Well, we've talked about 3 different kinds of processes now. ISO this is and ISO that's. ISO cores, isotherms, isobars, isocores. There we go. We've talked about those, but there's a lot of other kind of processes. But right now we're going to talk about work. I really like little w the best, but let's review about work a little bit here. Work is force times distance. Do you remember that from your high school physics class? That work is force times distance. And if you're using metric system, it's newtons times meters. And a newton times a meter is equal to a very special unit in the metric system. We'll go to Spencer. We'll pick on Spencer again. Spencer, what's the unit for work in the metric system?
Joules.
You got it. Jolly good. Now, if you're in the English system, they don't use newtons. We'll keep picking on Spencer. He's got a good attitude and he's a good sport. What is the unit in the English system? It's not Newton, Spencer. What is it?
Is it slugs?
No, slugs is a unit of mass in the American customary. We don't use American customary. We use English engineering and SI. Did you know there's really 6 different systems out there of units? One of the older ones is the CGS. When you give your horse a shot, you give cc's. So many cc's. Does that ring a bell, anybody? Anybody got horses out there?
Yeah.
Really? Who has horses?
Oh, my mom does.
Oh, okay. Well, I think you give cc's, don't you?
I think so, yeah.
Yeah, cubic centimeters. Well, see, we don't use that system either. And we don't use slugs. That's American customary. So what is the unit in the English for force? Let's pick. Let's start with Roxana. Roxana, what's the unit for force in the English engineering?
I think it's pound force.
Yeah, there you go. Good going. Pound force. And Roxana, what is the unit for distance in the English engineering?
Feet.
Yeah, good going. It's the foot. So the unit for work in the English system, Roxana, what's the unit for work in the English system? Go for it.
I'm not sure about that one.
That's okay. It's the foot pound. Believe it or not, it's a foot pound force. Now, they have another unit for work in the English system called the BTU. And from memory, I think a BTU is 778. Oh, gosh. Foot-pounds, but we better look it up. I could be wrong. Go to the back and look up BTUs.
0.169.
No, it's not 1.169. Let me see if I can find it here. Go to the back and look up BTUs. And it says here a BTU, this is wrong. It's 778.17. I found that in table A.1. Can you find it? That's what they use for, well, they use both. They use foot-pounds force and they use BTUs. And here's how they relate those. Can you guys find that on table A1? Sounds like a steak sauce, doesn't it? A1. Guys, that's one of my best jokes that I have for you this semester, and nobody laughed. Well, that's the story of my life. Nobody laughs at my joke. Now, sometimes the force varies. It's not always the same. In fact, you could write force as pressure times area. You know what? You sure could. Because, see, what pressure is force divided by area. So force would equal pressure times area. But see, sometimes the force varies. And so your equation looks like this. The work is equal to, you have to integrate maybe an X or a Y or a dummy variable of distance there. DS will be fine. S stands for distance. But see, you could replace that F with a P times A. See what I did? F is P times A. See it? But see, ADS that's the change in volume. So work could be written as the integral of pressure times the change in volume. Well, we were talking about work earlier, that expansion work was positive and compressive work was negative. Well, there's the equation for work. There you have it. But we're really more interested in the little letters. See, the little w is equal to the big W divided by your mass. And if you take and divide this by mass, what you'll have is P d little v, because you're dividing through by mass. You're taking your volume and you're dividing it through. See, little v is equal to the volume divided by mass, and little dv would be the change in your volume divided by the mass. And so I think I told you before, the reason why the PV diagrams are so important is the area, remember in calculus, the area under your graph that's what this represents. This is the area under your PV graph. That's why PV graphs are so important. And we've talked about just had a senior moment again. Yeah, we talked about isotherms and isobars, but all the problems that we did today were with real gases like water vapor, saturated mixture water, R134A that you have in your air conditioners in your car. We didn't do any ideal gases. Let's do something with an ideal gas. We got time. We got lots of time. I got a half an hour with you guys. Let's use it. I want to do a problem with finding the work done. Just need some room here. We're going to use this formula here for work. Little w is equal to the integral of P dV. Okay. Well, let's do an ideal gas. Suppose you had an ideal gas, like air, for instance. And let's suppose the air is going. I'll make some stuff up. We'll do a pretend problem here, and we'll use this equation here. Now, if you had an isochore, there's no work done at all. Remember, the work done is going to be 0. I hope you understood that. That if you don't have any movement, you have to have a movement in order to work. You have to have a distance. See, the volume's got to change. And if the volume doesn't change, there's no work done. But suppose you had air, and suppose it's, well, let's do an isotherm. We're going to do an isotherm at I don't know, 50. I'm making this stuff up. 50 degrees Celsius, okay? And we're going to go from let's go from 200 kilopascals to I'm making this stuff up. Say 120 kilopascals. Okay, here we go. We're gonna make our isotherm now. Here's P, here's V. Now I could do this and put you guys to sleep, but see, you have to wake up sometime and figure stuff out for yourself. So I'm going to shut up for 2 minutes, and I want you to draw the process. We have an air. It's an isotherm at 50 degrees Celsius, and we're going from 200 kilopascals to 120 kilopascals. I want you to draw the process. Draw the process. I want to see a state 1, and I want to see a state 2, and I want to see a line going from 1 to 2 with an arrowhead on it. Now I'm going to shut up for a minute and a half, and I want you to do it, and then we'll see if we agree. Go. Well, I think maybe I gave you a minute and a half. Here's what I hope you have. I hope you have an isotherm that's kind of shaped like this. And I hope you put some pressures over here. See, that's your 50 degrees Celsius isotherm. And here's your state 1. And it's at 200 kilopascals. And here's your state 2. And it is at 120 kilopascals. And here's your process. You're going to go from 1 to 2. You're going to put an arrowhead on that for me. There's your process. Now, be honest. We'll pick on Parker. Parker, does your process on your PV graph that you did look anything like mine?
Yeah.
Yay! Good going. That's what it's supposed to look like. Now we're going to find the work done. That'll be fun. We'll do that in a minute. But first of all, let's get little v1. See, little v1 would be right here. And we'll get little v2. We'll take out another minute and a half and find those. Because see, really, to do this integral, don't you have to put in limits to go from v1 to v2? Isn't that calculus? Isn't that what they have to do in calculus? They have to put limits in there to do an integral, right? A definite integral. Now how are we gonna find v1 and v2? Let's go to my friend Roxana. Roxana, how are we going to get v1 and v2 if we know the temperature and we know the pressures? How are we going to do it, Roxana?
We maybe use the ideal gas law.
Yes, exactly. You're going to go P1 V1 equals RT1. And see, we know T1. And you can look up R for air. And we know P1. So you can get V1. And look at here, P2 V2 is equal to RT2. Okay, I'm going to shut up again for a minute and a half. And I need you to find these specific volumes. On your mark, get set, go. See if you can get them. And we'll see if I agree with you. Okay, well, I think I got V1 and V2. For V2, did you get 0.7729? And for V1, did you get 0.4637? Did I do those right? Mohammed, did I do those right?
I think that so, but I got 0.4635. I don't know. For V1.
Oh, that's probably okay.
Yeah.
I think maybe you rounded off or I rounded off. We're fine. What about V2?
Yeah,
Have you
that's
got it yet?
Yeah, it's correct. That's what I got.
How about the rest of you guys? Are you happy with that? If anybody needs me, we'll go through it.
I got a different answer, and I just want to see where I
Yeah.
went wrong.
Okay, now this is Bear talking. For which one, Bear? V1 or V2? Your answer was different.
This is Stuart, and I got a different
I'm
answer
sorry,
for both of
Stuart.
them.
I'm sorry, Stuart. Which one was different, V1 or V2?
I got a different answer for both of them.
Oh, okay. Well, here, let's do V1 together. Here's what you do. Stuart, I'm going to do this equation. Here we go. I'm going to go 200 V1 287. Now you have to add 273. I bet that's what you forgot.
Yes, that's where I went wrong.
That's where you went wrong. It's 323.15. If you do that, you'll get the right answer. You know what the difference is between an A and a B in this class? It's the difference between Celsius and Kelvin. You got to use Kelvin for a lot of stuff in this class. And if you use Celsius, you won't get the right answer. Okay, good. Well, we got that sorted out. All right, now let's find the pressure. I want to talk about this shape here for just a minute. Back in school, when you guys were younger and better looking, do you remember equations like this? XY equals 12, let's say. If you plotted that up, if X is 3, Y is 4. If X is 4, Y is 3. If X is 2, Y is 6. If X is 6, Y is 2. You get a graph like that. If this is X and this is Y, do you guys remember plotting graphs like that? X, Y equals some constant, and you get a graph like that when you did that in school when you were younger? What's the name of that? That curve has a fancy name. What's the name of it? Megan, do you remember what the name of that is?
Like a slope? Is that what you're going for here?
Usually slopes are just straight, Megan. This has got a definite curve to it. See, it's got a definite curve to it. And
Are you talking about like parabola?
Yeah, now you're talking, but it's not a parabola. See, a parabola, Megan, I know you studied this in school. Parabolas kind of go like that. You remember that? That's what parabolas do. This is not a parabola. Do you remember the name of it?
I don't think that I do.
Starts with H.
Hyperbola?
That's it. It's a hyperbola. This here is called hyperbola. And that's how come it has that shape. Because see, PV is equal to a constant if your temperature is constant, because it's equal to RT. And if the temperature is constant, then R is a constant, and R times the temperature is a constant. So it's sort of like X times Y is a constant, only it's P times V is a constant. So what you get is a hyperbola. If you have an isothermal process with an ideal gas, you have a hyperbola. Now we're going to get the area under here in a minute. See, this area here is equal to the work per mass on that process. And let's go through it here. I'll show you how to do that. We want to keep those numbers. We might need them. I just need a little room to work here. Yeah, there's lots of room there. I bet I got enough room now. Now, if in general, if PV is equal to RT, then P is equal to RT over V. Algebra students, can you get from right here to right here? P equals RT over V. I bet you can make it. So if we were to write this out, little w should equal the integral of RT over V dV from V1 to V2. Now I skipped a step. Are you okay with that? See, I plugged in that P in there. If you're not, just speak up. And now we're going to integrate it. And we're going to get the work per mass on that isotherm. Okay, students, that RT is a constant. You can pull it out, calculus students. And what you'll have is dV over V. Now, you know that. Mohammed, what's the integral of dV over V, Mohammed?
I think it's V.
No, it's not V.
V square over 2.
I want to know what the integral of dV over V is.
I don't know.
That's okay. You're here to learn. I know you know this though, Mohammed. It's the natural log. It's RT is a constant. Natural log of V. Then you have to plug in the units from V1 to V2. Hey, Mohammed, you remember that now, don't you? Natural log.
Yeah.
Yeah.
I remember that.
Yeah, you remember that. And so this is equal to RT natural log of V2 minus the natural log of V1. Or you could write it like this, RT, the natural log of V2 divided by V1. It's the same, it's an algebra thing. It's the same thing. Hey, we can do this because we know V1 and we know V2 and we know T and we know R. We can solve. Here goes. We're going to find the area, but we've developed a very valuable equation here for work per mass. Now this equation doesn't always work. It only works for an ideal gas isotherm, okay? But that's what we have. So here we go. I'm going to plug in the numbers and get it. Here we go. The work per mass is going to be RT. We know what R is. We know what T is. I think I erased it.
323.15 Kelvin.
Good going. Well, that's it. Plug it in and find the work per mass for me. And I will shut up for a minute or so while you do that. Well, I wonder if I did that right. I got an answer, but I want to see what you guys are coming up with. Let's see. I'm going to pick on Cameron if he's got it.
I'm still working on it.
Oh, take your time. How about my friend Bear? Bear, do you have it yet?
Still plugging in a couple numbers.
Oh, go ahead, plug. Plug away. What we're doing right now, anybody fell asleep on me, we're finding the work per mass. It's the area underneath this graph. And we come up with a lovely equation for it. And we just plugging in all our answers and getting it. How about my friend Aubrey? Aubrey, what do you get?
I'm not sure if it's right, but I got 47.38.
That's what I got. Now, Aubrey, what are the units?
Joules.
Almost. You're close, but they're not joules. Can you see the kelvins cancel? This is dimension.
Kilojoules.
Say
Is
that
it
again.
kilojoules?
What's the answer, Aubrey?
Kilojoules.
You're close. But no, it's not kilojoules. This is work per mass. You're leaving out the per mass.
Oh, kilojoules per kilogram.
There you go. That makes me happier. Now I'll put my units in brackets. I'm getting 47.38. Anybody else out there in the crowd getting that? I hope.
I also got that.
Yay, I bet that's right. That's 3 of us. Well, that's the work done. Now this is a curve. I've got 3 more minutes with you guys. I want to show you something. If you made this into a trapezoid and came straight down like that, and you took the area under that trapezoid, it's going to be a little bit bigger. Let me show you that. I don't know if you remember the area for trapezoids, but it goes like this. You go 1/2 the 200 plus the 120 times the difference between these two, which is 0.4637, no, 0.7729 minus 4637. I don't know if you remember how to do trapezoids, but that's the formula for a trapezoid. Now, when you do this, you're going to get an answer that's a little bit bigger because we don't have a straight line, we have a curve. Go ahead and plug that in and let's see what we get. And I'll show you, it should be a little bit bigger. Well, I got an answer. I'm getting a little w of 49.47. Notice it's a little bit, not much, kilojoules per kilogram, but it's a little bigger than the correct answer. See, this is the correct answer. This would be if it went for a straight line, but it's not, it's curved, and so you get less volume. Did that make sense? I'm hoping it does. Okay, well, it's sad, but our time together is coming to an end. Now, have any of you been able to successfully look at old, wonderful lectures on YouTube? Anybody?
Yeah, I looked at one last night.
Good for you. Now who am I talking to?
That's Spencer.
Spencer, tell the others how you were able to do that.
I went to the YouTube page that's linked on most of the homework assignments and found the lecture I needed.
That's right. Good for you. Now, sometimes it takes me a day to get those on there, so This here will be on YouTube, but probably tomorrow afternoon it'll be on there. But see, that's really wonderful. You can look at that and watch it over and over again. Wouldn't that be fun? Nobody said yeah. Okay. Well, we've come to an end here on our wonderful time together. Did you have any last words or comments? You know, you got stuff to do. You got homework, and you have an exam. That ought to keep you out of trouble. So you'll be working on that, but I will see you Wednesday morning for more fun. Now, we might have some time for review, but I don't have much time to try to teach you all this stuff, so we're probably going to launch into some new stuff on Wednesday also. But right now, is there any last words or comments before I find that little red button that I need here? I won't click it till you guys. Here's your chance. Any last words or comments? Okay, I'm going to blast off. 5, 4, 3, 2, 1, blast off. I'm blast.